We're in the home stretch now. Just a quick recap. In the first two lectures, I decided that this was an interesting problem in quantum field theory to think about. We're integrating out degrees of freedom in different regions. We're evaluating the entanglement entropy. One of the things we saw is that the result, the leading contributions depend on, to make sense of the calculation, we had to regulate it. And so I introduced a short distance cutoff. There's an area law term here with a power law divergence. Unfortunately, that's a very intriguing result, especially given what Daniel told us about black holes this morning. However, this constant depends on the details of the regulator, and so it's not just telling us about the quantum field theory. However, if we persisted here, a claim was that higher order coefficients can carry some universal information, and I tried to give you some flavor for the techniques or the tricks that we use on HEP-TH to do those calculations. I didn't get to talk about several things got dropped, but for the aficionados of killing vectors, those people who appreciate killing vectors, I didn't get to tell you a story about those, and so now there's an expanded homework, and there are a couple of extra problems that will appear. And Patrick's looking at me like, I mailed it to you before lunch.
Oh, I haven't checked my email.
Okay. It'll show up eventually. In any event, what I was talking about in the past two lectures is just background. John and I were quibbling about which 1994 paper took precedence in a certain calculation. And so that sort of dates the kind of material that I was talking about. And I wanted to move on to more recent topics. But I just wanted to say that much of in certain sense, the stage from the next two lectures was set by this interesting paper here, which is a short paper by our organizer, John Preskill. And it's called Quantum Information and Physics, Some Future Directions. And so it was written at a time when quantum information was certainly established, but it was established perhaps as a new branch of computer science. And I guess perhaps some of John's postdocs were physicists and they were worried that they were going in the wrong direction. And they wanted to be reassured. And so John wrote this paper where he, in quotes, he considered some promising future directions for quantum information theory that could influence the development of 21st century physics. So here we are in the 21st century. Two of the topics that he picked out in that paper were information and RG flows, which is what I'm going to talk about today, and then another topic was the holographic universe, which will be the topic of tomorrow's lecture. But like any good prophet, he was either misunderstood or just ignored. Certainly, I didn't know about this paper until 12 years later when one of my colleagues realized or finally understood what I was doing, and he pointed me and said, look, John said that was possible. But in any event, here we are in Jerusalem 14 years later, and John is still trying to get us to see the connections between quantum information theory and other areas of physics, and hopefully it's working this time around. So what I wanted to talk about today were possible connections between entanglement entropy, and trying to understand better the nature of renormalization group flows. But again, this is one of those topics which may or may not be familiar to people in the audience, and so I did want to spend some time trying to set the stage and give a brief introduction. To those of you who are completely familiar with this, I apologize for butchering it with a 5-minute introduction. And for those of you who are not familiar with it, I apologize for butchering this with a 5-minute introduction. But there are some references again, on the notes that are somewhere on the web page. And so if you're intrigued, you can take a closer look at those web pages. But if I just generally summarize what the renormalization group is about, it's just a systematic way. Oh, look at that. Let's say a systematic investigation of how how the properties of physical systems change when they're viewed at different energy or different distance scales. And the key idea is that the effects of short distance physics are going to be packaged in the parameters of an effective theory that describes the low energy physics or the long distance physics. And this is something that, well, perhaps quantum field theorists and condensed matter theorists are familiar with. And it's the material of grad courses these days. But it's something that actually has a long history and broad applications. Not just quantum field theory, but also turbulence. I'm told that, or I found, I read somewhere that road traffic can be discussed in terms of the normalization group. And actually last week someone told me that electoral systems can be discussed in the context of the normalization group. The material or the context in which I'm talking about it, though, is quantum field theory. And here the apparatus or the techniques that are talked about really emerged from, well, the HEP-TH folks, or, well, we weren't HEP, the particle physicists trying to put together a scheme or tricks to eliminate divergences in their calculations. But it was really perfected with the help of the condensed matter physicists who were thinking about systems near phase transitions. So what's the classic example in which we might talk about this? Well, I'm going to use an example that isn't a field theory as I present it, but rather a system of spins. And so the white X's here represent a system, a lattice of spins. And we might say that there's a Hamiltonian by which the nearest neighbor spins interact in some way, written here. And so every pair on the edges of the squares here will have some interaction energy. But then what I was instructed to do by Kadanoff, I guess, was to think about blocking the spins or replacing squares of spins by some effective spin at the center of each of these lattice cells, and then describing the physics as the effective physics of those spins. And there's a modified Hamiltonian, which I apologize might not show up quite well in blue. So the Hamiltonian of my effective spins doesn't have to, there's no reason to think that it has the same form, but we can expect that it starts again with a nearest neighbor interaction between an S alpha and an S beta here. There'd be some new parameter, K0 prime, but there might also be other kinds of spins or other kinds of interactions. So for example, this is supposed to represent nearest neighbor spins with a coefficient K1, and so that would be an interaction, say, between this spin here and this spin diagonally across over there. You might also have more complicated interactions, and so I've got a K2 here and some interaction with 4 spins, say in a plaquette. They may interact in some way. And so the basic idea is that if I want to think about these spin systems, in general I shouldn't just think about a single parameter, but I should think about a whole family of parameters. And so I would have any one of my Hamiltonians at some given scale described by some list of couplings like that. And what the renormalization group does is basically it takes us from some mu, when I do the spin blocking, to some new list of parameters or new list of values here. And there's some systematic approach by which I process everything so that I know that I start with my original parameters, I grind them through some machine, and I get the new parameters. Now the key or the remarkable thing, the reason this works so well or is so productive is that to make predictions to some given accuracy, it'll turn out that I don't have to keep track of an infinite set of parameters, but in fact there's only a few parameters that will be relevant or that will play an important role in, well, some particular calculation that I'm doing. So this is spins, or that's an example of how that might work with spins. I'll just say that in quantum field theory, you might see a similar effect if I'm, say, integrating out high momentum or short wavelength modes. You might, in your collection of Feynman diagrams, have an interaction like this. But if we integrate out, so this is something where I've got two phi cubed interactions. But if I integrate out high momentum modes in the exchange here, that'll naturally be incorporated into an effective phi to the fourth coupling. So the same sort of thing happens in quantum field theory. So the basic idea is I have at each energy scale or each distance scale, I've got an effective Hamiltonian or an effective theory described by some set of parameters. And so if we follow those parameters or watch them move around or watch how the theories move around in theory space as we do this integrating out, what we get are flows then. And so those are the famous RG flows. And so I've drawn some picture here. And so the arrows are following as I go from high energies down. So I'm integrating out short wavelength physics and going to longer and longer wavelength physics. Some nomenclature that is commonplace is just UV for ultraviolet. That's the high energy or the short wavelength physics. Infrared is the low energy or long wavelength physics. Now, an interesting thing about this picture is that the flows end or start and end at different points on the diagram. And so there are fixed points where the theory becomes invariant under scale changes. But of course, we talked about, or I briefly talked about, quantum field theories that are invariant under scale changes. And those are the theories that we call the conformal field theories. So maybe I should write that out. So from that perspective then, there are special places in the diagram which are conformal field theories, and then what we can do to fill out the space is perturb those conformal field theories by some interesting or relevant operator, and it'll take me along some flow in different directions around in the parameter space. There are different kinds of fixed points here. This would be an attractive one. All of the low energy physics drives me towards this point. This is a repulsive one. All of the operators here are relevant or drive me away. So this is physics at the UV. And then there are mixed ones here where some directions are attractive and some directions are repulsive. Now, yeah?
In this picture, what would be on the x-axis and on the y-axis?
So this would be G1, and this would be G2. So this is an imaginary field theory, and there are two couplings for some interactions in the theory.
So in the spin system?
So that would be like in the spin system I talked about kappas or k's, I guess. So, yeah.
Why is it called group, by the way?
Because there, well, in this nomenclature, there is really a group structure.
There's no inverse, though.
Okay. John, why is it group?
Bad name.
Bad name, okay.
Because Galman didn't know what a group was.
Ah, okay. Very good.
It's a state group.
Let's not worry about the name.
Do we need the renormalization to get the renormalization?
In principle, you don't, but that's a technicality. Well, I'm going to have to write that word on the board at one point, but I'm not so worried about that level of detail. Okay. One of the observations, well, this is just a cartoon, but an observation is that these flows have some structure, or that there are restrictions. For example, there are no flows or circular flows in this diagram. Here I can go to this point, and that'll take me to this point, but there's not a flow that takes me from here up to here. And so it seems that there's, well, some interesting structure that restricts the behavior of the theories in these RG flows. And so we might try and use information theory to try and understand that structure better. However, even before information theory came on the scene, at least for 2 dimensions, the structure, or a very elegant structure, was discovered on the space of 2-dimensional quantum field theories. And where did my eraser go? Oh, okay. So actually what I want to do is go like this. This is all, there's a plan here. Okay, and so what are we talking about here? Well, we're talking about 2-dimensional quantum field theories. We're talking about the RG flows. And what Zamolodchikov discovered was that there was a special function that lives on the space of different couplings here. And so this is some positive real function that I call capital C of G, where G denotes my couplings, and it has some interesting properties. First of all, it's monotonically decreasing along the flows. And so, well, this is the way that I'm going to, I'm not going to explain this equation, but this is saying what is said in words there. It's also stationary at the fixed points. So C is decreasing as I move along any flow here. When I get to the fixed points, and so those are places where the theory is scale invariant, or so any couplings in the theory stop changing. So that's described in terms of something known as the beta functions. But it turns out that that C is stationary, so the derivative with respect to the couplings at those fixed points vanishes. And it's also true that when I sit at the fixed points, I said here that I'm looking at a 2-dimensional conformal field theory, but that capital C then equals the central charge of the corresponding CFT at the fixed point. One of the...
I don't know if you said it was one, this is for 1 plus 1 dimension.
Two, yeah, well, okay, for me, 2, so 1 plus 1, yes.
Renormalizing.
Okay, what? Yeah, I think I said it.
All right, I missed it, sir.
So as I was going to be told there, that one of the nice things about this is that there are, well, there are assumptions made to come up with this idea or to prove this result, but they are very basic apple pie assumptions as far as the readers of HEP-TH are concerned. So the basic inputs are that the QFTs that are studied here are unitary. I'll say that they're Lorentz invariant, although that's not quite the way, well, yeah, that's a detail I won't worry about. And then there's something which I'm not going to explain, that they're renormalizable quantum field theories. But the interesting thing then, or one interpretation, is it takes this flat picture here and turns it into a 3-dimensional picture, which I am now going to amaze you with. I guess I needed another mountaintop over here. And then down in the valley we have So in some sense, we've got some kind of, this flat picture gets turned into a landscape where the elevation in the picture is just measured by this C function. Now, a very simple corollary or consequence of this, well, all of this structure here is a simple inequality, which is if I look at an RG flow that connects two different fixed points or conformal field theories, then, well, this CFT, so this is at the upper end, so I'll say that's the ultraviolet CFT. It has a central charge CUV, and similarly at the other end, the infrared end, I'll find another central charge, which, because C is changing, is different, but there's an inequality. That says that the central charge, well, the central charge up here, or the elevation up here, is bigger than the elevation here. The flows are always downhill. And so comparing the two CFTs, I find that the central charge has changed in that particular way. And this is something that then became known as, or is commonly referred to, well, I'll call that the C-theorem. And so, following John's question, can we use entanglement or can we use information theory to understand the C-theorem from a different perspective? And so the answer to that question is yes. And it was provided in 2004 by some work by Cassini and Huerta. So and so what did they do? Well, they provided an alternate derivation of the C-theorem for two-dimensional quantum field theories. But their assumptions were slightly different. So again, unitarity and Lorentz invariance were key building blocks. But the last thing that they used was actually strong sub-additivity. Strong sub-additivity. And so I'll remind you that I can write this last as an inequality for entanglement entropies involving a system with three components. So my three components I'm calling X, Y, and Z. So here I have the entanglement entropy of the union of the three components. I'm going to subtract and then add, and that quantity is supposed to be positive. And so that's a rather surprising result. I mean, if I look at, well, I'm going to talk about it, but if we look at the construction, even though it's a result that applies for, it's describing something about the properties of quantum field theories, most of the construction that I'm going to be talking about is actually geometry, or the interesting new part is actually geometry. Rather than some detailed or complicated field theory calculation. C is a very special parameter that's going to characterize our two-dimensional quantum field theories. One way to see what it is it would be a parameter that characterizes the leading singularity in the operator product of two stress tensors. Alternatively, it's the parameter that we saw last day in the entanglement entropy. So I wrote something for the entanglement entropy of a CFT, and here we were looking at an interval of length L on an S1. So the full space-time geometry was S1 cross time, but we can look. So we take a time slice. The time slice then is a circle. In what I'm going to write here, the circumference is 2 pi r, and I'm going to think of an interval. My A is going to be this interval of length L in there. And so I had a result last day that had a C over 3, so the prefactor involved this central charge. That's the same C. And then there was a logarithm that had some interesting geometry in it. There's 2r over delta sine L over 2L, or L over 2r. So what I want to think of, or what they want to think about, though, is just the Minkowski space where I can apply Lorentz transformations. And so what we want to do is we want to think about taking the limit that r, the size of the circle, goes to infinity, but I'm going to keep L fixed. And so we can see what happens here is that this argument of the sign is becoming very small. And so at the end of the day, we get an expression like that. Oh, sorry. Yeah, this is r going to infinity, L fixed. And so this is the result that's appropriate when I'm thinking about, now this will be a diagram, space-time diagram. Remember, we're in 2 dimensions. There's time runs up, x runs across. We're going to pick our time slice just to be x equals 0, say, or t equals 0. And then we've got some interval here of length L. So this is the result that we're going to play with. So the first observation is that I can manipulate that in a simple way and just isolate the central charge. If I take this result, the entanglement entropy for a conformal field theory, and I take the derivative with respect to L, well, that's just going to pull out a 1 over L here. And so I'll multiply by L just to get rid of that factor. Also multiply by a nice factor of 3 just to get rid of the 1/3. And so that isolates then the central charge of our conformal field theory. Yes.
So that entropy, divergence of entropy is related to something.
It's related to the fact that there are an infinite number of degrees of freedom. We should worry about that a lot. And if I get that far, I'll spend some time talking about that. Okay? Okay. But we're actually doing fine. So what I would like to do, or what they do, it's not, is define a C function for general field theory. So now I'm not just talking about a conformal field theory. I'm talking about some general field theory. So it might be some UV field theory that I'm perturbing with a relevant operator. And so there's some interesting flow underlying our calculation. But I'm just going to define this quantity where this is now the general, or the result for the entanglement entropy in this general theory. But what we've seen, or what this tells us, is at the fixed point, we're going to recover then the central charge of the theory. And so what they go on, and I'll talk about this, what they go on to prove is that this new function that we've defined here is, that its derivative is negative, i.e. if I expand L, or if I expand my interval, I'm going to, it has a negative slope. It's always going to be decreasing. And so if I can prove that, that would be then an entropic version.
As you've written it, it's slightly stronger. You have it strictly decreasing.
Yes? Well, we can do that. That's fine. There's an issue which, again, I may get to later on, having to do with, I'll get to it when I get to it. Let's see, this is a big mess. So this is an entropic version of the C-theorem. And one of the things I can note, though, is, usually, the discussion here, or Zamolodchikov's discussion somewhere, a field theory discussion, usually we're talking about energy scales. And here, what we've got is a distance scale. So L appears as a proxy for that, the energy scales that appears in the usual discussion. But our intuition is, again, the standard intuition in our field theory is that energy scales are inversely proportional to length scales. And so what we can expect is that when I have a very short length for my interval here, that I'm probing short distance degrees of freedom, or high energy degrees of freedom in the theory. But when I extend my interval to be very, very large, then I'm going to be probing the theory at long distance scales, at low energy scales. So I'm just making a note of that. Then what do we do? Oh, we have to make some further observations. Yeah.
I would have thought that changing the cutoff and then growing the length of L relative to the cutoff would be more analogous to integrating out small ultraviolet degrees of freedom rather than just changing the length of the interval. If you just change the length of the interval, you're not throwing anything away, are you?
I guess, no, as you phrased it, I'm not I'm not integrating stuff out and I'm not throwing stuff away, but what I'm doing is I'm probing the theory at a different scale. And so, I mean, if I if I look at a scattering cross section, what I can do is I can look at low energies and I can see that there's an effective potential with, or I can describe it in terms of some effective potential with a certain parameter. If I do the same experiment at high energies, I see that I can again describe it with an effective potential that maybe goes like a Coulomb potential, but I had to change the coupling, and so I mean that's sort of at the heart of the renormalization group, but sort of the way I phrased it, I'm not really, there I'm probing the system. I'm not actually doing a calculation where I integrate out degrees of freedom and tell you what, how that coupling changed. And so this is, I guess this is more like an experiment that I'm probing the theory, and I'm getting numbers coming out of the experiment. And so C is my measurement.
Can we say it this way, that when you have a CFT, each scale of length is contributing equally to the entanglement entropy. Let's say the theory is flowing, so you get an effective description when you get to longer and longer distances, and you're finding that increasing decades of scale are making smaller contributions to the entanglement entropy.
Yeah.
Until finally you flow to the new CFT, and then it stabilizes again.
Right.
Contribution for each decade of scale.
Okay.
Which again is invariant.
So that's another way of describing the experiment. It's like, well, yeah, okay.
This is kind of
Sorry.
a very closely related question. So yesterday we were talking about the area law, where you make a cut and the entropy across, the entanglement across the cut measured by the entanglement entropy is constant independent of the size of the region that you've snipped out. And that was in the gapped case where you do have a scale. That seems almost like in conflict with this, where you're the places where this derivative of the entropy with respect to the size of the region you're snipping out goes to zero.
Right.
In the gapless case. So it's
No, in the gapped case, it went to zero. Is that what you mean?
yeah.
Wait.
The area law seems like it's telling you this should be zero in the gap case, and then the conformal field theory thing that's the gapless case, right?
Right. But if you like, the gapped case, what I have is a correlation length or a mass scale, and then I'm going to probe down here, but there are no degrees of freedom left over. And so in this sense, then I've gone to an empty theory, and the central charge has gone to zero.
Oh.
I mean, if I probe the theory at energy scales below the gap, I'm not going to get it to respond.
Okay, yeah.
What did I want to do here? Oh, okay. So the standard discussion that we were having here, or that I was presenting of entanglement entropy calculations, I took a constant time slice, and I picked two endpoints on that time slice, and we did some calculation. I'd like to be slightly more adventurous and introduce the idea of an initial value surface or a Cauchy surface that doesn't have to be a constant time slice. So here's my time, here's my x. And so there, that surface, it's not a constant time slice, it's not a constant time slice in anybody's frame, but it's a good initial value surface if I'm propagating my wave function or propagating some wave equation from there. So on that surface, we might also, there's some state of the quantum field theory on that surface, and so I can pick an interval, and I can try and evaluate the entanglement entropy of that interval. However, an interesting observation is that I could have also picked some other Cauchy surface. That was a little bit steep, but that's less than 45 degrees, that went through the same 2 points. And the claim is that, well, the evolution of the theory is unitary, and so it shouldn't matter whether I chose this surface or this surface. I'm still going to get the same entanglement entropy. In some sense, this is related to the idea that I talked about last day, that the density matrix controls the physics not just for correlators, say, on this surface here, but in fact describes the physics inside the causal, some kind of, well, what I called the causal development, or the causal, well, here it's a causal diamond. Here my diamond gets slightly tilted because the tilt or the choice of points over there. But all of those density matrices on any one of these surfaces are going to lead to the same entanglement entropy. A further observation, maybe I should write that down. So I'll call that E1 and E2 for my endpoints. So the entanglement entropy is going to depend on the endpoints and not the details of the choice of Cauchy surface or initial value surface. Another comment is that we're not studying this in some excited state. We want to be thinking about the vacuum. And so by translation invariance of the vacuum, in fact, we should be, or we can argue that it's not the endpoints that's really relevant, but what's relevant is the proper distance between those 2 points. And so I'll remind you, if you needed reminding, that in Minkowski space, when we talk about proper distances or distances between points that are separated both in space and time, the proper distance means this combination of things. So I take the spatial distance squared, and I subtract the difference in time squared, and then we square root it. So I'm always going to be considering places or configurations where this set or combination of things is positive, and so that square root makes sense. Or alternatively, where my endpoints are spatially separated.
So these two Cauchy surfaces, they're related by a Lorentz transformation of Poincare.
No, I would have to do some kind of local unitary evolution to get between those 2 slices. I mean, these aren't constant time slices in anybody's frame. So that sort of sets the stage then for oh dear, strong sub-additivity disappeared. But we're going to apply strong sub-additivity. The interesting thing they do is consider the following geometry. So here are my axes. Here's t equals 0. I'm going to pick one interval here on the t equals 0 slice, and we'll say it has length L, and so this point is times 0, L over 2. This point is times 0 minus L over 2, and we'll call that interval y. I can then, what I'd like to do is I'd like to move forward to another time slice. So this is t equals 0. I'm going to move forward to t equals epsilon. But I'm going to move forward to that slice, but I'm going to shoot it out in a light-like direction. And so we're going to end up at a point over here where I'm now at epsilon, and I moved outward from this point by an epsilon as well. And we're going to do the same thing in the opposite direction over here. X. So this is epsilon minus L over 2 minus epsilon. And so there were various entanglement entropies in that expression. One involved the union of x, y, and z, and so that the endpoints then are these 2 points up here. But over there I argued that that should just be a function of this, well, the proper distance, which is now just the spatial distance from here over to here. And so that's S of L plus 2 epsilon. There was an S of y, but that's just S evaluated at, again, it's a spatial separation, so it's S of L. So they're just the 3 components. So there's the spatial slice, those 2 null slices. But when I evaluate this, you know, I'm going to bend the Cauchy surface, or what we, you know, I can equally well think that I'm just evaluating it here, or I can say that what was relevant is the proper distance for the separation of those 2 points. And I'm supposed to consider this. But that's equivalent, well, those, again, those depend on these 2 proper distances, or alternatively I could evaluate the entanglement entropy on those time slices. But those distance, well, I put an equal there because those 2 distances are the same. And, well, there's a formula here. The spatial separation, I go forward L plus epsilon, and I go forward an epsilon. So if I plug in that formula there, what I get is that it's the square root of L times L plus 2 epsilon, or L squared plus 2 epsilon times L. And so you might, well, I don't know if it's important, but you might note that what is this? That's the first the small separation times the large separation under the square root. But what we would, or what we're instructed to do next then is consider the case when this epsilon is becoming small. Well, no, first of all, let me, okay, I'll write it all out. So we had that inequality. I'm going to just plug in these numbers, but then I'm also going to take the limit that epsilon is becoming small. And so, for example, here, that first one is going to be then S of L plus 2 epsilon times S prime evaluated at L plus, well, 1/2 2 epsilon squared S double prime of L plus dot, dot, dot. So there's some Taylor series that represents that, where what I'm doing is I'm just saying there's a function, S of L, and I'm expanding around L. And then there are two other, well, the last one is just S of L. That's the S of Y. I have to do the expansion for the two unions, or the expansion here. But what I find at the end of the day is, well, all of the terms that were order epsilon to the 0, there's an S of L here and an S of L here. There are two S of L's hidden in that bracket, and so they cancel out. Similarly, if you look at the first order terms, those also all cancel out. And so the first non-vanishing term is order epsilon squared, and what you have there is S double prime plus 1 over L S prime. Sorry?
Some inequality between geometric and arithmetic means that underlie. Never. There's
There's-
always an inequality that the arithmetic mean is larger than the geometric.
Oh, okay. Maybe that's at the heart of this. What I was going to say is what we ended up with, I could write as this, or alternatively you can think of that as the derivative of L times S prime. And so the only thing I'm missing here is my factor of 3, but I can write that then as this entropic C function has is that going? There's a sign that went wrong somewhere. Oh, this is the other way around? Oh, excellent. Thank you. Saved by Patrick. Thank you. Well, this is just then an example, an interesting example, where we can apply tools from information theory in an interesting way, and we find some result, that restriction that the quantum field theories have to obey.
It holds for every density operator, always. Yeah, there are lots of different ways. The original proof was through complex analysis, maximum modulus principle.
Every density, I mean, the only restriction is positivity trace equal to 1.
Yep.
Sure.
So, at the heart of the derivation, it seems like we use the entanglement entropy depends on the proper distance. Not
Yeah.
Can we prove it? Or is it, did you prove it? Or?
Well, I argued that so we were working in the vacuum, and first I argued that it only depended on the endpoints of the interval, wherever they were in the space-time. And then I argued that by translation invariance, it should only depend on the separation. But in our relativistic theory, we talk about the proper distance rather than, well, any other distance. So that was the motivation that was sitting here on the board for a while before I went over there. One question, well, maybe I should pause. Are there other questions? Yeah.
I maybe more of an ideological comment, but I think that so renormalizability is not necessary for the theorem, as this version shows, and also for Zemologikov's version, there's a version where it's obvious that you don't need to talk about coupling normalizability.
Okay. Thank you for that comment. Any other comments, questions? So this was deriving or rederiving, presenting an alternate perspective on something that was known already. A natural question or a direction to go is to ask, there was a C-theorem in 2 dimensions. People were struggling to prove C-theorems in higher dimensions or thinking about proving higher dimensional C-theorems. In particular, there was a lot of interest in 4 dimensions. The reason for that is that in thinking about C-theorems, people were again guided by, or a lot of the intuition, they were guided by the trace anomaly. As I described, the trace anomaly is something that depends on being in an even dimensional CFT. And so after 2, the next natural thing to look at was d equals 4. Carty made a conjecture very soon after Zamolodchikov's work that there is a certain central charge known as A, which should have some nice properties or be, satisfy an equivalent theorem for RG flows in 4 dimensions. It turns out that there was a lot of struggle to prove that, but it was proven just in 2011 by Komagardsky and Adam Schwimmer nearby at the Weizmann. But that proof has nothing to do with entanglement, and so if you want to learn about it, I encourage you to go read about it on the archive. Instead, a place where entanglement seems to have provided some guidance is thinking about odd dimensions. And so in particular, this is a place where the trace anomaly vanishes, and so we had no guidance as to what might serve or what might be a useful central charge to consider in renormalization group flows. It turns out that holography gave us some clues or suggested a particular entanglement entropy calculation where the entanglement entropy calculation revealed a quantity that would be effectively a central charge that had some interesting RG properties. And I'm going to focus on the case of 3 dimensions because, well, I'm just going to tell you about 3 dimensions because there was a proof that came out just in 2012. And this is the same Cassini and Huerta, and hopefully I wrote down the paper somewhere. Oh. So this is 1202 5650. Yeah. So that is open question number 1 on page 11. Right now we're on page 7. Well, I can, why don't we wait until I get to page 11 and I'll comment on that. So what is the, in their paper, in their original, the paper before from 2004, they said, wouldn't it be interesting to go to higher dimensions? It seems like a natural thing to do. But one of the problems was, well, in 2 dimensions, now my entanglement surface is a line, and it has some interesting geometry. And the question was, well, which geometry should we pick out? And they just shrugged their shoulders and said, we don't know. So it turns out that the interesting geometry, it turns out, is just a circle. And so the idea is that I'm going to pick my t equals 0 slice. So this is t equals 0. Now there's an x, there's a y, and I'm just going to evaluate the entanglement entropy for some circle. But I'm going to let the size, well, they're going to let the size of the circle vary. If I evaluate this quantity for a CFT, I'm going to get an answer that has an area law term in it. I guess I called that delta tilde before. If you look at the power series expansion that I described before, the next term would go down by 2 powers, but that would be then something with a positive power of delta. And it skips over the fact that, in fact, there can be a finite contribution. And so I'm going to write the finite contribution in some way like this, where there's some parameter A sitting in there. And so I'll remind you, this is not universal. But the claim is that this is a universal constant that, that characterizes the conformal field theory. And the corresponding C-theorem is that if I'm thinking about some RG flow between 2 fixed points, if I evaluate that constant in the UV, and I evaluate it at the IR fixed point, that there's an inequality that looks like that. Something that you should complain about or worry about is that before I talked about logarithms, and there's a lot of intuition that we have perhaps that logarithms are safe, that the coefficient there should be a universal constant. This here is just a constant term, whereas it's buried behind this divergent term. You might worry that we're going to be able to subtract off this area law term in a unique way and identify this in some consistent way. And I'll let you worry about that for a few minutes while I make other comments. But I will return to that question.
Is that the derivative of C with respect to L?
I'm sorry. Yeah, this was a derivative. Yeah.
That means at L equals 0 is the maximum, we have maximum value for CL.
For very, very short, yeah. Then I'm probing the short distance physics, or the UV end of the RG flow. And so I expect that it goes to a constant. There's going to be problems in taking it right to 0, but if we think of it as being very, much smaller than any mass scale in the problem.
We have a maximum value for
Yeah.
It's a terminology thing. What's the difference between a C-theorem and an A-theorem?
There's no difference.
Okay.
Although a lesson that I will learn, or I will teach the students in the audience at some point, that it's important to come up with a sexy name for your theorem. Well, yeah, we'll leave that story for a couple of minutes. Yes?
Here, the entanglement entropy, do they have the same thing as in 1 plus 1 dimension, that it is proportional to the proper area maybe? And that's how I choose my...
Oh, yeah, I'm not really going to talk about the details, but at the end of the day, well, yeah, I mean, it will be, yeah. If what they're going to look at in this proof is you're going to look at this, well, various circles in different frames, And what's important is the proper circumference or the proper radius of the circle. What did I want to say? Well, I guess their proof is a clever extension of what they did in 2 dimensions. In this case, we can define a C of R, which is slightly more complicated. But you can see if I'm sitting at a CFT and I take that derivative and then multiply again, what I've done is I've isolated this term, and then I do that subtraction. The area law terms cancel, and what I'm left with then is this is the 2 pi a. Or at. So that's something, again, that we can evaluate or try and evaluate for a general field theory. And we expect that at small r, we're probing the short distance physics. We're going to see the A of the UV CFT. At large r, we're probing the long distance physics. And we're going to see the physics, or the A there, of the ultraviolet CFT.
The sense in which the C measures the number of degrees of freedom there is two-dimensional.
Yeah.
Just from, counting the number of photons and twice the number of fermions. Does A have an interpretation like that as well?
That's a great question. I don't have any intuition for that from the perspective of field theory. I do have some intuition for that from the perspective of holography, but I don't think I'm going to be talking about that in either today's lecture or tomorrow's lecture. So if you'd like to ask me afterwards, I'm happy to talk about it. I think at this point I'm just going to say there's some complicated geometry that they go through. In this case, as I alluded to, what you're thinking about is evaluating this circle entropy in different frames. It turns out that you actually, well, if you think about the intersection of two, or the intersection or union of 2 intervals, that just gives you an interval. When you think about the unions and intersections of overlapping circles, you get some more complicated geometry. And so they had to have they made a construction where you're actually taking some limit with an infinite number of circles. And that, well, that's one complication. The other complication is that overlapping circles, the geometry has kinks in it. And you might worry that the kinks provide extra contributions beyond the kind of contributions that I'm seeing here. However, you're able to argue that away for the particular configurations that they're considering. But I think I'm just going to have to leave you to read the paper to see the details. Some other comments are that, well, I called it a C-theorem, but it's commonly known as the F-theorem. And that's coming from the work of Jeffries, Klemenoff, Pufu, and Safdie. And they were working completely independently. They were originally interested in supersymmetric gauge theories, but their observation or their construction was to evaluate, so I have my favorite, well, if I'm looking at the CFT, I have my favorite conformal field theory in 3 dimensions. I go to the Euclidean and I evaluate the partition function on a particular geometry, Euclidean geometry, which is a 3-dimensional sphere. you can, well, then you throw in a logarithm and a minus sign, and that gives you some positive constant. And what they observed in studying at first well, some supersymmetric examples and later other field theory examples was that this F had, again, this inequality or this property that it was always larger. It seemed to be larger at UV fixed points than it was at IR fixed points. And so they conjectured well, they made this a broader conjecture that it should apply not just in supersymmetric gauge theories, but it should broadly apply to three-dimensional quantum field theories. And they went on to find evidence by studying perturbed conformal field theories and other non-supersymmetric theories. It turns out, well, you might think that it's hard to find quantities that satisfy an inequality like that. And it turns out that this inequality and that inequality are the same, up to the factor of 2 pi that I threw in over there. So it coincides with the entropic version. And I won't go into the details, but that was something that I showed with Cassini and Huerta. The interesting thing about the chronology and the naming is that Aninda and I made our conjecture using entropy in 2010. We said in this paper in February of 2011 that the entropic version would be equivalent to something where you evaluate partition functions. And then it was a month later that they came up with this conjecture that said that the partition function, or this F, but the key thing that they had was a really sexy name. And so that's the thing that stuck. And so that's an important life lesson for all of the students in the audience. Yeah.
But in the C-theorem, the theorem doesn't specify the function theorem. It's just specifying the property of the C that it should decrease.
Sorry?
It should decrease on the renormalization group flow.
So there are various versions. I would say this is the weak version of the C-theorem or A-theorem or whatever. I'm just focusing on the endpoints of the flow. You can also ask that there be a quantity that flow, as sort of the C function that Zamolodchikov defined, that flows monotonically as I go down the RG flow. That's not been established. No, I guess it has been established for this particular quantity. I mean, this particular quantity.
Yeah, but my question is, can someone find another function that has the same property? It's possible, right?
Oh, yeah, no, I'm given a monotonic function, you can play with it and you can build lots of other monotonic functions. Is that what you're saying?
Yes.
Okay.
Even in 2 dimensions, right, the Cassini-Huerta C is different from the Zamolodchikov C when you're not fixed point, right?
Right. In general, yeah. But again, if you're given a monotonic function, you can play with it and build other monotonic functions. So it's not really a new, well, I don't think of it as a new thing. Yeah.
For y is a universal constant, what do they mean with these universal constants? Rather, you take only circles and you...
So the complaint that I had before about this constant was that if I and my grad student did the calculation and we used slightly different, regulators, or we regulated the problem in slightly different ways, we would have come up with different values for that number. And so... Yeah, it's what goes into the delta here. And so the question is, well, a general comment is that, on HEP-TH, when people are doing calculations, say, of a cross-section, you run into various divergences and you have to regulate your theory. But then what you do is you work hard to absorb terms that are potentially divergent into other parameters of the theory. And so you describe then, or you combine them into the physical couplings of the theory, or the physical parameters, and you describe your answer in terms of those physical couplings. But then at the end of the day, you take the regulator to infinity. The physical couplings are finite. They're things that I'm supposed to measure. And so these kinds of calculations are very much in contrast. Here we have a divergent term, and it just sits there. And I'm not trying to, well, it's just because there are an infinite number of degrees of freedom. I'm not providing a prescription that says that I absorb this in some other parameter of the theory. And so these kinds of calculations in the standard field or the standard HEP-TH calculations are very different. And I have to confess that meant that for 4 years I chose to ignore entanglement entropy because it had to be rubbish. But I came around after a while. But the question is, does it really make sense to talk about this as a universal constant? Is there really a unique way to extract or remove, this is buried behind something that's very, very big. Can I really get rid of that big part and identify A in a unique way? And the claim is that it's yes. And so there are two versions of the story that I'll tell. One is by Hong Lu and his student, I think, Marc Mazet. Essentially, what they observed was that if I construct the theory with some kind of covariant regulator or geometric regulator, then the entanglement entropy in general has some form with, well, the form that I so that's a C naught, the C2. So this is an expression that I wrote down before that describes the leading terms in the entanglement entropy. I can imagine doing it, say, for a sphere. So there's this is the area law. What I said is that this term also had a simple geometric interpretation in terms of an integral over the entangling surface and various curvatures. And that proceeds further on. If I'm doing this for a general theory, then there are other scales in the problem as well, having to do with dimensionful couplings. And so these coefficients here are going to depend on those couplings. And they have to be dimensionless coefficients, so I can arrange it all so that it's the coupling or a mass scale times my short distance cutoff. But the observation is that all of the geometry or all of the R dependence appears in these geometric terms in a very organized way in the entanglement entropy. And so the suggestion is that you can isolate, well, whatever term you want in that expansion by doing various derivatives. Well, in fact, I've got the formula right there. So, for example, if I'm in 3 dimensions, well, I'm just rewriting that formula there. So if I'm in 3 dimensions, there's going to be an area law term, there's a finite term, and then there are terms that vanish according to the cutoff, or positive powers of the cutoff. And this combination is going to isolate then that finite term. But you can play the same game in any number of dimensions by applying more and more derivatives and taking appropriate combinations of derivatives and, well, powers of R, et cetera, et cetera. And so this, then in general, well, this particular case, var, a comment is that in general dimensions, one finds that this prescription for a C function doesn't work. What does that mean? It means that you identify a C function, but in various systems you know or you find that it's not monotonic, that you're not going to satisfy some kind of inequality that, like that one at the top of the board over there. No, what we're thinking of is flowing away from a conformal field theory. So we've so you can think that you're starting at a conformal field theory, and all the couplings there are dimensionless, if there are it. But then I'm going to add some relevant perturbation, and so that's what I'm doing is I'm adding an interaction, but the coupling constant for that interaction is going to have a scale in it, and so I've just glibly called that scale mu. And then I'm following what happens to the field theory as I flow away. So these mu's aren't associated with the fixed points, but rather they're associated with the stuff that's appearing in the middle of the flow over here.
Expression for entropy. Can we identify these couplings from the original CF and the CF mass or rather interaction?
Can you identify?
Mass or any?
Why don't I'm not sure I have the answer to that. I think the answer is yes, but I'm going to take that question offline just so I can wrap up. Yep, we did that. So just as a few comments on an alternate approach to thinking about it, although I'm really just going to be talking about 3 dimensions, although similar, well, you can have a similar discussion in higher dimensions. Here there was a proviso that, there was a proviso that I needed a very special kind of a regulator, a covariant regulator, or a geometric regulator. But you might think that if this is really a physical constant, or this A is a physical constant of nature or of quantum field theories, that any regulator that defines the continuum limit should be a good regulator, and I should be able to define that A. So let's think about a lattice regulator. I'm going to write that same formula again. Now, so here I have my, well, I'm trying to draw a circle. I have my square lattice of coupled harmonic oscillators. I'm trying to draw this circle on there. I'm going to, if the goal is to evaluate the circumference, what I'm going to do is I'm going to find that the circumference is equal to 2 pi r plus corrections, where the corrections are going to be of order delta. So I'm calling my lattice spacing delta here. And I can refine my lattice and make delta smaller and smaller, and I'll get a better and better approximation to what 2 pi r is. But there will always be corrections, or there'll be an artifact of the lattice will be that the best I can do is get an answer to order delta. And if that's the goal of the question or the goal of the calculation, that will suffice in that I get a better and better approximation to the answer. However, here what I'm doing in the entanglement entropy is I'm taking the circumference and I'm dividing by delta. And so what that says is that these corrections that are appearing here in the lattice calculation are always going to feed over or spill over into the finite part of the answer. And so it would seem then that the lattice regulator is never going to be able to give you a proper definition of that constant if all I'm doing is evaluating the entanglement entropy. So in S. And so that seems to be a problem, but another perspective is then that we need a better idea. And so a proposal for a better idea is that we not focus our attention on entanglement entropy, but we take some other measure of entanglement. And so an interesting measure might be the mutual information. The reason it's an interesting measure is that it is just a finite quantity. A simple way to write it is if I have two non-overlapping regions, I can write, or I can evaluate it as the entanglement entropy of each of the regions minus the entanglement entropy of the union. Or that's, yeah, I'll leave it like that. It turns out then that this structure, you can build a natural regulator for this particular problem. What I'm going to do is I'm going to take one region to be a disk. I'm going to take the other region to be the outside. So I'll call that A. B is going to be the exterior here of this bigger circle. There are two radii here, R1, R2. There's a separation here, epsilon. And the prescription I'll offer is that R1, 2 is some capital R plus or minus epsilon over 2. But the key thing is that these are both macroscopic scales, and I'm going to take them to be much larger than the lattice or the cutoff scale. It turns out then that when I evaluate this quantity, I get a finite answer. And I get something that looks more or less like the answer that I have there for the entanglement entropy, where that epsilon, or this short, the separation between the two circles, plays the role of the cutoff. But there's a geometric term, and there's this 4 pi, there's the constant term here that's independent of epsilon and independent of r. It turns out that that's precisely the same constant that we identify there, up to a factor of 2. The 2 is just basically because there are two circles here rather than one. And you can, in simple models, you can take them and you can put them on the lattice, and you can see that we're trying to evaluate this with entanglement entropy isn't converging, that this actually very quickly converges to give you a finite answer here. And you can also extend the discussion of the A-theorem or the Lorentz transformations and all the complicated geometry that I didn't talk about before. You can discuss in the context of this construction as well. Which means that I'm 5 minutes over, and I'll ask John, can I have 5 more minutes? I may. Excellent. So all that, well, what I think that we're seeing here is just the beginnings of the connection between information theory and RG flows. And so this is hinting that John was pointing us in the right direction, but there are, I think it is just the beginning. And so there's a number of questions that one might ask, or where one might hope to apply these kinds of ideas to get a better understanding of, or a, perhaps not a better, an alternate understanding of various aspects of RG flows. And so I had a list of questions. The first one was, what about higher dimensions, that Paul asked us about? So in that case, you might think that I can just extend the construction that I had in 2 dimensions and then in 3 dimensions and think about what happens in, say, 4 dimensions. The complication is that if I'm working with spheres now, I have higher dimensional objects, and the intersections are more complicated or more interesting. And in particular, you can find, if I have 3 spheres intersecting, there are various, there are various cusps or conical defects that you wouldn't have seen before. Before you had one kind of singularity, now you have several kinds of singularities. And it turns out in the straightforward application, you just end up with strong sub-additivity saying infinity is bigger than 0. And so it's not a very useful. But that leaves it in my mind as an open question. Are there more interesting geometries? Are there other ways to apply entanglement entropy, perhaps to apply or to have some kind of mix between other field theory ideas and these kinds of ideas to prove a C-theorem in higher dimensions? I focused my attention on what I called the C-theorem, or what might be called the weak version of the C-theorem. Another question is how much of Zamolodchikov's structure actually lifts to higher dimensions. So here, I don't know if we had hinted at this already, but one of the questions, or one of the properties of the C function, was that at the fixed points it was stationary. So the derivative with respect to the parameters of the theory was going to be 0. But it turns out that there's a slight problem in that this was Klemenov, Nishikyo, I'm probably mispronouncing his name, and then Sylvia Pufu and Safdie. What they showed is that this is not the case, that the d equals 3 entropic C function is not stationary in complete generality. So what they did is they just looked at a massive scalar field theory and looked at the UV end of the RG flow, and they showed that the derivative was still negative there. It didn't go to 0 in the limit that the radius, well, the mass times the radius was going to go to 0.
Does the A-theorem imply that all that structure lists to 4 dimensions?
No, it doesn't. It's I mean, all we've proven, well, actually, what you've proven here in this number of dimensions is you've, well, not the, I'm pointing at the wrong thing. I've identified a C function that at the fixed points is equal to this quantity that we're calling the central charge, and it's monotonic. But the stationarity was an extra, or the third, or in the list it was the second property.
So
And so, well, no, here it's showing that it's not in complete generality. It's not, it doesn't hold. You might still ask, is that sort of the generic, is being stationary a generic feature? Or does it almost always hold? Or is it generic that it's not stationary?
Is there anything else other than the monotonically decreasing and fixed points being CFTs or stationary?
Well, those were the three properties that I listed for Zamolodchikov's C function way back at the beginning.
So I missed, what was the third property?
Stationary.
Yeah, so it was monotonically decreasing, it was stationary, and it equaled at the fixed point, it equaled the central charge. What's another question? So, well, another question is, I mean, I've assumed so far that scale invariance equals conformal invariance. I.e., if I have my favorite relativistic field theory and it exhibits scale invariance, that symmetry should actually extend to local rescalings or to conformal invariance. That's something that's proven, and it follows from Zamolodchikov's work in 2 dimensions. It's proven to within reasonable doubt in 4 dimensions. But in general, well, again, it's a question that you could ask about 3-dimensional RG flows, or you could study flows beyond 4 dimensions if you were interested in them. And it's related to the question, you know, do RG flows always start and end at fixed points? Can they do more interesting things? Can there be some kind of chaotic behavior here? Can you have limit cycles? And it seems, well, in most examples where you assume things like Lorentz invariance unitarity, that those last two are not allowed, and that's related to the fact that this actually does seem to apply.
Sorry, did you say proven with reasonable doubt or without reasonable doubt?
To within reasonable.
Within.
Unreasonable doubt? I don't know. It's not a.
Does that mean we
It's not a. You can believe it. However, I know that in the last talk I saw, I forget how Zohar phrased
Some
it.
mild technical points, and they point out, you know, like when it breaks down. It's a recent paper from someone got two others.
Tyson and the unnamed grad student. Okay. Yeah.
So
Name.
I actually had a thing to say about scale invariance and conformal invariance.
Okay.
So the ways that people will go about trying to prove that scale invariance implies conformal invariance very much depends on local currents.
Sorry, depends on.
Very much depends on local currents. So
Okay.
if you're talking about a theory that was non-locally scale invariant, I think it's actually entirely unclear how to show that conformal invariance is local.
Okay.
Well, I mean, yeah, so the normal intuition that it should follow also doesn't exist there. So I was wondering how that would affect A-theorem, F-theorem, things.
Well, I guess you would have to define your theory, and we'd have to understand exactly what you mean by non-local. In particular, you know, well, yeah, beyond that, I'm not going to say anything, because I do want to quit, or I want to let you go to coffee. So number 4 here, I just put the word majorization or majorization. This is an idea that various people have played with in the mid-2000s. But just very briefly, and it's the question is, you know, we've looked at one quantity that we've uncovered in the entanglement entropy, but can you say anything about, well, what they try and do is they try and study the behavior of all of the eigenvalues of the density matrix. And there's some kind of majorization if you compare the density matrix at different points in the RG flow. However, that's a subtle thing. Again, it's going to, you know, the density matrix, like the entanglement entropy, is only going to make sense when there's a regulator in the game. And so one has to be careful on how to make sense of that. And then the very last question that I put here is put your own favorite question down and answer it. And so with that, I'll call it quits.